Let's look at tutorial question number 5. Glycine is the simplest amino acid that exists. Question wants you to draw the structure of the glycine zwitter ion. So what we will do is when given the structural formula of a amino acid and you're asked to draw the structure of the zwitter ion, it's actually very simple. Okay, you just have to remember that the N terminal, which is your amine group, will be protonated with the hydrogen ion, and then the acid group on the right hand side, okay, will be dissociated to give you the carboxylic acid, carboxylic ion, I beg your pardon, right? So that will be effectively like an internal proton transfer. Okay, so the structure of the zwitter ion, you can draw it in the skeletal drawing as shown, or you can produce it in the structural formula, write it in the structural formula as shown on the screen as well. So one thing to take note of here is the placement of the positive charge. It should be on the nitrogen atom, okay, instead of on the hydrogen. Okay, next in part B, you are asked to the type of reaction that occurred in reaction 1 and 2, as well as the reagents and conditions required for the changes that took place. So let's look at step number 1. Now, upon inspection, you should be able to notice that the part on glycine, right, is observed to be at this part of the structure of K. So this end of compound K, okay, is now like newly introduced or would have been likely from your other reactant required in reaction number 1. We also would have made an observation of the presence of the amide functional group here. Okay, so and we have an amine end here, and we all know that amines, right? The lone pair on a nitrogen atom on the amine group can be a good lone pair donor, so that function as a nucleophilic end. So in order to get a amide from amine, okay, we will react acyl chloride with an amine. And so the structural formula of the acyl chloride will be thus what we observe. It will have to be a benzene ring followed by a C atom with double bond. And so this will be your acyl chloride that is required to form the amide shown in K, right? So the C atom here and your Cl atom here is polar, and so that's why your amine would be able to come in to attack the electron deficient carbon of the acyl chloride to form amide. So in order to do this reaction, okay, you will need the reagent shown already. So the type of reaction, there are two possible answers. Either you state it as a nucleophilic substitution or nucleophilic acyl substitution, or alternatively, you can have a condensation, state it as a condensation reaction. So the reagent I've mentioned already, right, is your benzoyl chloride. And here it's important that you avoid mentioning um, so-called AQ, right? Or if the system has a aqueous media given, you would not be able to use the acyl chloride properly because your acyl chloride will readily hydrolyze in any aqueous medium as well, right? So do take note of this. So in step 2, okay, the observation here would not you should notice lah, by observation that the amide group is no longer present. Here you have a secondary amine form from your amide, and then you also have a primary alcohol that formerly where you have a carboxylic acid. So knowing your organic chem reactions well, so when you have a carboxylic acid becoming a primary alcohol, this is a reduction reaction, right? So amide can also undergo reduction. So here the reaction for 2 would then be a reduction reaction. And the reducing agent that you require will be your lithium aluminum hydride. Okay, so that will be your type of reaction as well as the reagent and condition required for step 2. Next, we move on to part 2. Draw the structure of compound J. So as you observe here for compound J, the formula given is C6H11NO2, right? And then your glycine began with 2 carbons, right? 2 C atoms. And then you notice that next to the arrow for reaction 3, we have 1,4-dibromo butane, right, which contain a total of 4 carbon atoms. So I think that would appropriately describe or help us figure out that uh, there's no other reactants that contains carbon atom involved over here. Okay, and then we also see that there is a nitrogen atom and 2 O atoms formed, okay, present in J. So if we were to also look at the reactant provided, bromine, it's going to cause your CBr bond to be polarized on the left side as well as on the right side of the molecule, right? So your 1,4-dibromobutane is effectively like one molecule having 2 alkyl halide functional group. So imine, as we mentioned earlier, has a nucleophilic end on the alpha amino group, right? So your lone pair on a nitrogen atom of amine functional group can effectively come in and attack either of these 2 electron deficient carbon atoms. Okay, so what's going to happen here is either one of them can be reacted with. So if we were to, let's say, make it undergo a nucleophilic substitution reaction, we will end up having this intermediate form. Let me draw it on the screen. Okay, so let's say we begin the reaction with the C atom on the left side. Then you have your COH. Okay, and then you have your CH2, 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 and Br. Okay, so your carbon and bromine is still a polar bond. And right now, what we have is a amine. Now we have a secondary amine. Previously, it was a primary amine. So this is a stronger nucleophile, okay, than before. So what will happen next is that your lone pair on a nitrogen atom will then be able to come in to attack the electron deficient carbon atom on the other end of the molecule. Okay, so that would effectively close the form a loop or form a ring, okay, in your structure. Okay, so let's look at the structure, how it will look like. So to draw this structure, you need to take note of the total number of carbon atoms. We have 4 of them, which are highlighted in yellow. So the 4 C atoms are over here. Okay, and the nitrogen atom that we have used previously, okay, as the nucleophilic end, okay, is this N atom here. And then of course, whoops, I think I drew it wrongly. There's one group. It should be a CH2 and then a COH, right? So there's one more carbon N, right? One more CH2 group. So that would constitute this part of the chain, right? Highlighted in green in color, right? So this will be your uh, chain formerly from your glycine. Okay. So those of you who actually drew only the straight chain intermediate shown on the screen here, all right, that will be a wrong answer. Okay, so you can actually verify this by checking the molecular formula given by the question for J, right? So let's say if you were to stop here, right? the total number of carbons in our intermediate, if you were to go and count it, right? So you have, let's say 2, 4, 6, 8 here. Then you have one more here, 9. Oops. Okay, 9. And then you have two more here, 11. And then one more for the acid, you have a total of 12. Right? So if you just give your structure for J as such, right, it will not agree with the molecular formula of 11 hydrogen atoms for J. Right? So that would require you to think one more step ahead, whereby so now you have 12 hydrogen atom. So how do you make one more H atom loss, right? Is by actually getting rid of the H atom on the amine by forming a tertiary amine. Right, so this compound that we have here is a tertiary amine. So the hydrogen atom formerly found on the N atom can actually be substituted out when the lone pair attacks the electron deficient carbon on the right hand side of the CBr bond. Okay, so this question here is not so straightforward. You need to be mindful of the increasing strength of the nucleophile being formed as an intermediate. Okay, moving forward for part 3, you have a scenario whereby a student proposed the reaction of benzamide with chloroethanoic acid to form compound K. The validity of this proposal or the underlying basis of this proposal can be examined from the structural formula of chloroethanoic acid. Maybe I just draw it out. Okay. And then you have a COH. So, and then your benzamide has a structure that looks like this, right? C double bond O, and then an NH2. Okay, so your compound K has an amide bond being formed. So effectively, it's asking you that if we were to apply what we have done earlier, which is to take the polar CCl bond, all right, and then the lone pair on this N atom here to make it undergo a nucleophilic substitution reaction with the electron deficient carbon. So the question is whether or not this will happen. So over here, we need to then look at the characteristic of the amide functional group, which is the C double bond O and the N atom, okay, which are all connected together. So as we have learned, right, the lone pair on the nitrogen atom of the amide bond is actually delocalized to the CO group, right, the neighboring C double bond O group. So that makes the lone pair unavailable. Oops, sorry, let me just, right, okay. So if the lone pair on the N atom is not so readily available, that means your amide nitrogen will not be a good nucleophile. As such, the formation of compound K would not be possible, okay, via nucleophilic substitution. Okay, so over here, our conclusion here is that the lone pair on N atom is delocalized into the pi bond of the adjacent C double bond O by resonance. So it's not available to donate to the electron deficient carbon of the CCl bond. Okay, so here, just take note of the bond of the characteristic, okay, of the amide group, okay, in this topic. So that'll be the end of this video.